Outside the window of a passenger airliner at 10,000 meters, the environment is deadly. The temperature outside drops below -50 degrees Celsius. Due to low atmospheric pressure, a human loses consciousness here in just 30 seconds. Yet, inside the cabin, hundreds of passengers breathe calmly and feel completely safe. It seems logical that the plane carries massive oxygen tanks, like a military submarine. But aviation engineers know that the weight of such tanks would make the flight impossible. Instead, the air you breathe is taken directly from the center of a screaming jet engine. Before reaching your lungs, this air is compressed and heated to +250 degrees Celsius. This is the strict physics of the bleed air system, hidden from ordinary passengers. In this video, we analyze how a system designed to create engine thrust keeps you alive in the sky. Let us look at the exact technical figures of our atmosphere. At sea level, normal atmospheric pressure is 760 millimeters of mercury. But as the aircraft climbs past 3,000 meters, the air density drops fast. At a cruising altitude of 10,600 meters, pressure drops to a critical 170 millimeters. The percentage of oxygen remains 21%, but the space between molecules increases. Human lungs cannot expand enough to capture oxygen at such low pressure. To survive, the aircraft cabin must be constantly inflated from the inside like a balloon. Automation maintains an artificial cabin pressure equivalent to 2,000 meters above sea level, and the only compressor powerful enough to do this is the jet engine itself. The mechanics of the bleed air system follow strict thermodynamic laws. First, a massive titanium fan at the front sucks in huge volumes of cold air. The airstream then enters the low-pressure compressor stages. Next, rows of small titanium blades force the air into the high-pressure stage. Here, the extreme mechanical compression causes the air temperature to spike. Engineers tap into this airflow before it mixes with aviation fuel in the combustion chamber. At this point, the extracted air temperature ranges from +250 to 450 degrees Celsius. This extreme heat instantly kills all bacteria, making the air completely sterile. However, pumping this scorching stream directly into the cabin would burn human lungs instantly. To cool the air, it is routed to the technical bay located under the aircraft fuselage. This area houses the complex air cycle machines, technically known as the packs. The hot engine air first passes through primary heat exchangers. Here, it is cooled by the freezing ambient outside air without ever mixing with it. Next, the pressurized air enters a high-speed expansion turbine. As the pressure drops sharply, the gas cools down to a comfortable level according to physics. The output is stable, a clean airflow at roughly +15 degrees Celsius. This air passes through medical-grade HEPA filters to trap any microparticles. Finally, it enters the cabin mixing manifold and flows through the overhead vents. The absolute safety of bleed air relies on the integrity of internal engine seals. Carbon seals keep the pressurized cabin air separate from the synthetic engine oil loop. In March 1953, early jet airliner tests revealed a major vulnerability in this design. A microscopic structural deformation occurred in a right engine oil seal. Under high pressure, synthetic turbine oil leaked directly into the hot compressor stage. The 300-degree heat caused the oil to undergo thermal decomposition, releasing neurotoxins. A toxic chemical mist bypassed the air conditioning packs and entered the cockpit. The flight crew experienced sudden spatial disorientation and acute respiratory irritation. This historical incident forced regulatory bodies to create strict seal inspection intervals. Yet, the phenomenon known as aerotoxic syndrome remains a hidden reality in aviation. Official ICAO data shows that oil-related fume events still occur once in every 2,000 flights. When a seal fails, toxic fumes reach passenger seats within a matter of seconds. This chemical risk is the price paid for a continuous supply of oxygen at high altitudes. The air conditioning system pumps air inside continuously, but it must also escape. If the air cannot escape, the rising internal pressure will rupture the metal fuselage. To prevent this, engineers installed a crucial component in the tail, the outflow valve. Thanks to this valve, the air inside the cabin is completely renewed every 3 minutes. A computer regulates the valve. If pressure drops, it closes. If it rises, it opens. In essence, an airplane is a dynamic balance where air inflow strictly equals air outflow. But if a mechanical single point of failure breaks this chain, a disaster begins. On August 14, 2005, a tragic maintenance error proved the danger of this system. Helios Airways Flight 522 was preparing for a routine flight from Larnaca to Athens. Before takeoff, ground engineers conducted a manual pressure test on the cabin doors. After the test, a technician forgot to switch the pressure control back to automatic mode. The pilots failed to notice the manual setting during their pre-flight checklist. As the Boeing 737 climbed, the outflow valve in the tail remained wide open. The engines pumped fresh air in, but it instantly escaped out into the vacuum. At 3,500 meters, an altitude warning horn filled the cockpit with a loud alarm. Confused by hypoxia, the pilots mistook the horn for a takeoff configuration error. At 5,500 meters, emergency oxygen masks deployed automatically in the passenger cabin. These chemical masks provide oxygen for exactly 12 to 15 minutes. This time is calculated for the pilots to perform an emergency descent to 3,000 meters. But the pilots, severely affected by oxygen deprivation, lost consciousness completely. Controlled only by the autopilot, the aircraft turned into a silent ghost flight. The plane climbed to 10,400 meters and flew until its fuel tanks were completely empty. All 121 people on board died because of one single toggle switch left in the wrong mode. While safety is paramount, bleed air is a massive financial burden for airlines. Mechanical air compression requires huge amounts of energy from the engine shaft. Extracting air before the combustion chamber cuts engine efficiency by 3 to 5%. Across a global fleet, this small percentage burns millions of tons of extra kerosene daily. For decades, transport corporations accepted these losses as an unavoidable operational cost. No alternative engineering solution existed until digital design changed thermodynamic laws. In 2011, Boeing introduced a radical departure from tradition with the 787 Dreamliner. This aircraft became the first commercial airliner to abandon the bleed air system entirely. Instead of using the engines, fresh air is drawn through dedicated vents in the belly. For powerful electric compressors compress the outside air for the passenger cabin. The jet engines now only generate electricity, keeping their internal airflow intact. This architecture recovered the lost 5% efficiency and eliminated chemical fume risks. Synthetic engine oil can no longer physically contaminate the passenger breathing loop. However, an all-electric design demands a massively complex power grid. It requires heavy lithium-ion batteries, which introduce their own technical hazards. This is why standard narrow-body planes like the Airbus A320neo still stick to classic bleed air. Aviation history demonstrates that at 10,000 meters, there is no room for compromise. Every breath you take on board is paid for by a calculated balance of physics and finance. It is a hidden, dangerous infrastructure working flawlessly to keep you alive where humans cannot survive.